I'm okay, but still I am much fragile compared to the pre-pandemic time. Health is also not still 100%.
Yes, again, well soon. Professor Balu, are you there? I just saw him.
He is not there, I think. Now he might have
left.
No. I request him to chair the next session. We'll just start the next session in a minute or so.
Is Balu chairing the session? Do you want me to give him a call?
Yeah, I just gave him a call. So
Yeah.
So Professor Balu, are you there?
Good. Yeah, it did not allow me to unmute for some time.
Oh, okay, sorry. So the
That's
next
the problem.
talk, it's by Professors Zurab, Janelidze and Amartya Goswami. So I would request you to chair the session, Professor Balu, if you can. So the Professor Zurab is from Stellenbosch University and Professor Amartya is from University of Johannesburg. And today they will be talking about duality for groups revisited. Professor Balu, I will request you to continue with the chairing session.
Good. Let me greet you all for this session, where Amartya Goswami and Janelidze will be talking on duality for groups. Please go ahead. Can you share your screen?
Yes, is our screen visible?
Yeah, it's there.
Okay. Thank you, Zurab. Thank you very much, Professor Ramachandran, and thank you very much the organizers for this invitation. And it's a great pleasure for us to give a talk in a BRICS conference. And specifically for me, it's a little bit nostalgic because it's this year it is happening in India. And after some long time, I'm seeing some faces which I met long time ago, like the last speaker, Professor Shamli Gui, in 2004 in HRI, and as well as Professor Dipendra Prasad, also in the same year at HRI. So with this sweet memory, let us start our talk. And currently I am in South Africa at the University of Johannesburg, and Zurab is from Georgia, and he's currently at Stellenbosch University in South Africa. Both of us actually very interestingly met mathematically through Zurab's father, very renowned category theorist in the world, Professor Janelidze from University of Cape Town. And so our collaboration was very interesting, and with this relationship, we actually grown up with different areas, specifically in the category theory and categorical algebra. Okay, so with this introduction, let's go to the actual problem. So this whole talk is actually starting answering a question, which the question has been asked more than 70 years ago. So that question actually came from Saunders Maclean, one of the founders of this category theory, along with Samuel Eilenberg. And the question what he asked in his duality for groups paper is actually noticed that certain theorems for the group theory, specifically these isomorphism theorems, actually can be done with respect to the subgroup lattices without mentioning or using these elements. And in this paper, he actually mentioned this about this duality arises in these theorems which not actually need these elements, but subgroups and the homomorphisms are sufficient to do that. And in order to study these dual behaviors of these groups, he started with a set of axioms. But immediately he mentioned that for the development, giving the first and the second isomorphism theorems and so on, can be made by introducing additional carefully chosen dual axioms. This will be done below only in the more symmetrical abelian case. So in Maclean's work, we see this duality has been studied in a more restricted cases for these abelian groups. For our wider audience purpose, we try to keep our language within the groups and group homomorphisms, although the whole foundation is very much categorical, and such that we are expecting that not only the wider audience as well as undergraduate students can also understand the talk what we are presenting today. So from here, Zurab, do you like to tell what is happening on the present day?
Thank you, Amartya. Yeah, so skipping many years since Maclean's paper in 1950 and going to present time, the work that Amartya and I did together and on which this talk is based. What we're going to do now is to give you a flavor of this work. So we propose in this work a self-dual context for working out homomorphism theorems for groups, a project that was left unfinished in Maclean's 1950 paper. There is a lot of category theory that kind of goes in between and has led to this work, including my own work with a student of mine, Thomas Wakel, which lay foundations for the later work that I'm presenting right now. Okay, so the first thing is to describe the language in which we will work. And although we will use the usual group theoretic terms, these are supposed to be considered as abstract starting point. So when we say that, for instance, G is a group, we can think of this indeed stating that G is a group, but for us, this is one of our basic statements in this language. It doesn't have to mean that G is a group necessarily. It could be anything else as long as the axioms that we're going to explain later on are satisfied. Now, this context is self-dual, which means that any statement will have a dual version that's obtained by dualizing each primitive component of the language. So when we say that G is a group, the dual of that is still the same that G is a group. So this is a self-dual statement. The next primitive component of the language is F is a homomorphism. So here X and Y represent the groups, and the homomorphism goes from group X to group Y. And the dual of this statement will be that F is a homomorphism in the reverse direction from Y to X. So duality will reverse domain and codomain of the homomorphism. Then we've got here H is a composite of two homomorphisms, which in group theory has the usual meaning. And because of reversing direction of arrows in the dual version of this statement, the F and G will also reverse. You see here we have GF, and the dual of that will have FG instead. This is a theory that's built out of group homomorphism as the primitive starting point, but in addition to that, also subgroups are considered as part of the primitive starting point. So instead of defining a subgroup via, let's say, an injective group homomorphism, which is usually what's done in category theory, in this theory, being a subgroup is part of the primitive language. We will write it like this: S is an element of sub G, and the dual of that is still the same thing. So just like G being a group, being a subgroup is a self-dual statement. If we want to compare subgroups, one subgroup is less than the other, and then dual reverses that comparison. So basically, the way duality works here is that every time things are being compared, whether it's via a homomorphism or inclusion of subgroups, that comparison is being reversed. So one can think of it like that. Then we have also, as part of the language, we have when one subgroup is a direct image of another under a group homomorphism. So if we have a group homomorphism F and subgroup A of X of the domain and B of the codomain, then we'll write B equals F of A and say that B is a direct image of A under F. And the dual of that will be the inverse image. And vice versa, the dual of inverse image is direct image. Okay, so this is the language on which we will impose some axioms and then be able to prove theorems. But before stating the axioms, let's introduce some derived notions that can be expressed using this basic language that will be useful. For instance, an identity map from a group to itself can be defined using this usual property. Then being an isomorphism is something we can express with the language that we just described. We also want to have smallest and largest subgroup of any given group G. Note that we will write the same G for the largest subgroup of G. And then we want to have a notion of image of a group homomorphism, and that will simply be the direct image of the largest subgroup of the domain, as expected. And we also want the notion of a kernel, and that will be the inverse image of the smallest subgroup. And now, according to the duality principles we stated in the previous slide, we will now see that the dual of the direct image construction ends up being the kernel and vice versa. And this is a very important point in the theory, which enables self-dual approach to group homomorphism theorems, namely the point that image of a group homomorphism and its kernel are dual constructions to each other. Then there is a notion of a normal subgroup. As expected, it's a subgroup that's the kernel of some group homomorphism. And the dual notion will be conormal subgroup. That will be a subgroup that's an image of some group homomorphism. But of course, in group theory, every subgroup, in the usual group theory, every subgroup is conormal. And so that's why we don't see conormal subgroups in ordinary group theory. But here we want to separate them because if we had required here that every subgroup is conormal, then because of duality, we would also be forced to require that every subgroup is normal, which we don't want, because then we will not be able to talk about non-abelian groups. So we distinguish conormal subgroups among all subgroups. Okay, so the axioms can be organized into 5 major axioms. The properties that we want to impose can be organized into 5 axioms. They are very, very usual things that we all would agree, any group theorist would agree that they're very basic facts about groups and group homomorphism and subgroups. So here we have axiom 1. For example, part of axiom 1 is associativity of composition. And we have axiom 2, which where this property here, a group theorist will recognize that that property is the so-called lattice isomorphism theorem. Note these notations here. So this represents meet of 2 subgroups, which usually is normally intersection. And this one is join of 2 subgroups, which of course is not just the union of them. We have also this stability axiom that requires that join of normal subgroups must always be normal, and meet of conormal subgroups in a dual way must always be conormal. Now, I haven't explained all the axioms here, but I don't think it's necessary to do so. The idea is that all these axioms are quite basic. And each of the axioms is actually self-dual relative to the duality we described before. So let's say, for example, if we take associativity, we reverse all the errors, we still get associativity. This property here, for instance, which establishes a Galois connection between direct image map and inverse image map, is itself also self-dual. Okay, so there are two more axioms. This axiom here, the realization axiom, This is the one that allows us to view every subgroup as an actual group. And this is how we will write it, S/1. And we're requiring that we also have this canonical embedding. And by embedding, I mean that it will have a certain universal property. The property is that the image of that must be less than S. It will actually imply in the end that it is equal to S. So this is the group, the subgroup S represented as an actual group with the subgroup inclusion map here. And the universal property says that if there is any other group homomorphism, F, such that the image of F is also less than S, then that F must factor through that embedding in a unique way by some map. So this map exists and is unique. And the dual axiom to this will allow us to form quotient groups. So if I have a normal subgroup S, then I should be able to quotient that out, and then we have the usual universal property for the quotient map. So the universal property for the quotient map becomes now dual to the universal property for the subgroup inclusion map, which is also an important point in the theory. And finally, we have this first isomorphism theorem as one of the axioms. It says that if I begin with a homomorphism F, I can also always factor it as a composite of the quotient map and the embedding. But if I have initially fixed one quotient map for each subgroup and one embedding for each other subgroup, then I might not end up in exact decomposition. I might have to involve an isomorphism that connects them. So just a technical, for technical reasons, we're involving this isomorphism H, nothing significant. We could have as well dropped that and just required this instead. Okay, so these are all the axioms. So we've got just like 5 axioms. Now, out of these axioms, we will be able to derive basically all homomorphism theorems of groups that are known to be true for non-abelian groups. And let's talk about how this can be done. To do that, first we will have to introduce in this language the idea of subquotient and exact sequence. And at this point, I pass back to Amorto.
Yeah, the whole idea here is that, as Zurab mentioned, that in a normal group theory, every subgroup is a co-normal. But here, when we say that B is normal to A, that means these 3 conditions will be satisfied, that B is a sub of A, and A is co-normal. And when you take the inverse image under this embedding of this B, and that should be the normal. And the standard way of writing these subquotients will be A/B or A, depending on the our choice of the notations. And every subquotient we can actually represent it by in terms of this embedding and the combinations of these projections as is written there. So G is our group, and then we have this embedding and of the quotient A by 1, and then we have this the other quotient on this other side, which comes through these projections. So this is a very fundamental definition of for our theory, because very often in most of the theorems, the objects are in this form of the subquotients, where these conditions need to be satisfied in order to be called them the subquotients. And the next is exactness, which is as expected definition in the usual sense that we say that a sequence is exact and object Y, or in our case it's a group Y, if the image of the first homomorphism is equal to the kernel of the second homomorphism. And we will use these exactness conditions, or rather this general exactness idea, to prove these diagram lemmas of the homological algebra. So with this set of axioms and these terminologies, so let us try to apply these chasing things. We try to do it for the Salamanderlemma, and Salamanderlemma is one of the most recent diagram lemma in homological algebra due to George Bartman. And this lemma is formulated for the double complexes in the sense of as we see is quite common of this appearance of double complexes in the context of spectral sequences in the study of algebraic topology. So this Salamander lemma is about proving a very long exact sequence where we see these subquotients in the sense as we have talked in the previous slide. And in this long sequence, if you see the second one and the third or fifth one, these two are the standard horizontal and vertical complexes. So these are already known things. So Bergman's actually introduced more homology objects in the sense of the other subquotients. So we can directly do this chasing, and for doing that, we need to do two things. We need to construct these connecting morphisms between each of these subquotients, and then we need to prove this exactness in the sense that the image of the first one is equal to the kernel of the second one. But if we do directly that way, then it is quite lengthy because we need to construct this connecting morphisms using this chasing. So instead of going that way, we try to formulate a general result such that this Bergman's lemma will come naturally. In some sense, the proof will become trivial in the sense that if we go to do this chasing directly, then we have to do individually for each of these connecting morphisms as well as proving this exactness. So instead of that, let us take two group homomorphisms for this general theorem, where we have this F and G are the two homomorphisms and it satisfies this hypothesis which we needed, and along with this normality conditions which is written on the second bullet. And the whole idea is that when you take in this sequence of the subquotients morphisms, then it will be exact in the middle place if and only if this following identity is satisfied. So two advantage, of course, we will go through this proof or sketch of the proof. It is a little bit involved, but the advantage of it that once we set up this stage using this Salamander trap, then not only it helps us to prove the Salamander lemma of Bergman's diagram lemma, but it actually gives an algorithm for generating other exact sequences for double complexes. And whenever we will have in future any kind of diagram lemmas for double complexes, we need to just check the last conditions, what is written here, that identity is satisfied, and then we can immediately get these exactness conditions. Okay, so let's see how we can actually prove this Salamander trap. Okay. Of course, this proof is quite involved with respect to different axioms, what Zurab actually explained before, and several consequences which have been derived from these axioms. But let us try to give a layout of one of the chasing. For example, what do we want? We want actually connecting morphisms between uyv to wyx, from wyx to yz. That's our first proof. The second is we need to prove the last dotted arrows f double prime and g double prime is actually exact. That sequence is exact at w over x. Okay, so first to get this f double prime, we need to get some morphisms f prime. And how to do that how to get that f prime? Okay, here we use this universality property what Zurab mentioned of this embedding iota w. And remember that in the hypothesis, we had this f of u is a subset of w. And that immediately gives us to use this universality property of this iota w. And thanks to this universality property, we immediately get this f prime such that the top left square becomes commutative. Okay, so far so good. But for f double prime, this little bit more involved than getting a prime because it is natural that it's a little bit far from original morphisms, which is f. And for that, we wanted to use this universality of the projection map on the left-hand side, which is pi iota inverse uv. And in order to do that, we need to do some kind of chasing. And we need to show that it's when you chase this smallest subobject, the v, that when it landed at w over x, it must be 0. And in order to do that, we again use several results developed in our theory. And through that universal property, we get finally this f double prime. And again, the bottom left square is commutative. Similar way, we can get G prime and G double prime using the respective universal properties of the embedding and the projection maps. Okay, and once we get these connecting morphisms, F double prime and G double prime, which we first need, the final thing, what we need to prove that it is exact at W over X. What does it mean? We wanted to show that the image of F double prime is equal to the kernel of G double prime. And again, what is the procedure? The procedure is the chasing the sub-objects. Okay, so we chase the largest sub-object, U over V, which is the largest sub-object along this orange color arrows as it's going up. And then we use this map F, and then going on the right-hand side, we landed at H as a F of U. Then we go going down through the inverse image map of this embedding, and we landed up at these expressions as Zurab pointed it out as image of F double prime. Similarly, we take the smallest sub-object of y over z, which is the 0 at y over z, and chase back along the up, going through these projection maps, and then going along these embeddings, then take the inverse image of G and landed at H, and then going down through this inverse image of embedding, and then going down through these projections, and we get the other side. And of course, it's just a layout, and in order to get all these equalities, we are heavily used some of the results what actually we mentioned on the top portions of this. Okay, so this is roughly the sketch of the proof of the salamander trap. And using this, we can actually directly prove the Salamanderlemma, just checking this last identity as we mentioned in the previous slide. Okay, so okay, now maybe now Zurab will tell us that life is not so simple all the times as we are getting in the previous theorem, where universality was good enough to get the connecting morphisms. And in some places when things are not so well, we need further tools, and it will be explained with respect to other lemmas, but Zurab will tell the theory.
Thank you, Marto. So this proof of this lemma, I mean, we chose to show this just to illustrate how the proofs can look like. It does seem a bit involved in the beginning, but once you are a good master of the theory, then it kind of becomes not a very difficult lemma to prove. And that is actually thanks to the fact that each time that we wanted to generate the new arrows, like the F prime and G prime and F double prime, G double prime, they came out directly from the universal property of the other arrows that are involved in constructing the subquotients that we're trying to link up with these arrows. But this is not, life is not going to be so good all the time. There are many other homomorphism theorems where we can't use that method. And so here is one example, for example, the Zassenhaus-Lemma. By the way, this picture for the Zassenhaus-Lemma is something that came out from, I mean, there are many pictures for butterfly lemma. It's a well-known lemma, which is used to prove Jordan-Holder theorem. This specific picture came out from our, when we were trying to prove this using our theory. And so what we have here is that eventually we want to prove that these two subquotients are isomorphic to each other. And as it is usual, one goes via another one. So one proves that these two blue subquotients are isomorphic, and then similarly, one proves those isomorphisms marked like that, and then therefore we get an isomorphism by composing all this way. Now, to get isomorphism on one side, like of these two, we will have to do something similar to what happened before with, if I go back to this, in a sense, we produce this F double prime using this zigzag of arrows. But the sense in which life was easy there is that we were able to build it step by step. First, we produce F prime that came out from universal property of iota, and then F double prime from it, which came out from universal property of pi. But here, we will not be able to do that. So, for example, like there is nothing we can get here or here or anything like that. So we will have to produce this connecting arrow that will turn out to be isomorphic directly without being able to do those intermediate steps. So the question then is how to do that. And such obstacles arise not only in this butterfly lemma, also in other lemmas. Another example of this is the snake lemma, where we want to build a connecting homomorphism all the way that will come out somehow from this zigzag of arrows. Now, in the classical approach to proving these lemmas, in the abelian case, things work out nicely, because in the abelian case, when we have a subquotient of this form with inclusion and projection, we can always swap it around by push out and have it in the form of projection and inclusion. And so we can make it similar. We can make this similar to that one by swapping things around. And then we'll have a push out here, we'll have a pullback there, and then the argument goes via this middle arrow. So things become really easy. In the non-abelian case, we would take a limit over this whole diagram. And then this will actually represent the composite of these arrows in the zigzag seen as relations. And then we will argue about this relation. In the usual element-based proof, it's the same story. We compose these functions as relations, and then we'll prove that that relation actually turns out to be a homomorphism. And moreover, in the other case, in the butterfly case, something like that will be an isomorphism. But all of these traditional tools are not available in our context because, firstly, the swapping story with abelian case, where we can take push-outs and pullbacks, they don't behave very well anymore already in non-abelian groups. So that one is out. Taking the limit of this diagram, it doesn't work in our self-dual context because the colimit is not behaving similarly nicely as the limit is. So that one drops out. So we basically don't have any traditional tools to use to produce arrows out of these long zigzags. And so we had to develop something new for that. And this new thing is called the pyramid. And it goes like this. So if we have a zigzag of arrows connecting two groups, the left-hand side group and the right-hand side group, then we have to build the pyramid picture we see here. And the way we build this is kind of almost like combining, very much using the building process of this is very much using duality. So we begin by, we'll do it step by step. So, I mean, layer by layer. We will first see how we build this layer. So that's easy. We take each of these arrows and decompose them into a quotient map followed by an embedding. So the red arrows are going to be the quotient maps and the blue ones are going to be the embeddings. And such decomposition is possible thanks to the first isomorphism theorem, which is one of the axioms. Once we have done that, then to build the next layer, so the quotient maps will be arranged like this always. So we take their kernels, there will be normal subgroups, and we take the join of these normal subgroups and quotient out by that join. And that's where we need the fact that join of normals is normal. And then it turns out we get a diamond-shaped diagram where these are also quotient maps. So that's not difficult to prove from the axioms. So we get these red diamonds like this in the picture, which allows us to build up. And then for the other case, for the blue diamonds, they arise by intersecting these subgroups. So this subgroup and that subgroup, they will be intersected, and this will give rise to this diagram. In fact, the red diagrams are push-outs in the sense of category theory, and the blue diagrams are pullbacks. And so once we build that next layer, then we repeat the process. So then we can take this shorter zigzag and further decompose each by projection followed by quotient followed by embedding to get that layer. And then again, using those diamonds, we go up, and eventually the process will terminate. Now, a fantastic thing that happens here is that it turns out that if I have a subgroup here and I chase it all the way along from here to there, and what does it mean to chase? I think we never said what it means to chase, Amartya. So it means that along the homomorphism going backwards, I apply inverse image map. You know, along the homomorphism going in the direction of my chasing, I apply direct image map. So if I do this chasing in a horizontal way, and no matter what path I take, it turns out that the result is invariant of the path. So chasing along this way turns out to be the same as chasing all the way up and then all the way down. And then after that, well, first of all, that will be the case because the same is true for each of these diamonds. So these diamonds allow us to do something like that. And after that, it turns out that, okay, so if there was indeed a connecting morphism here, which is what we're trying to build, that behaves in terms of direct image and inverse image maps, behaves the same way as chasing along the zigzag, then because direct image of the smallest subgroup is always the smallest subgroup, so if I took the smallest subgroup and I chased all the way here, I should have ended up with the smallest subgroup there, right? If there was such a homomorphism. And also, if I take the largest subgroup, let's say this is group G, if I take chase backwards, inverse image of largest subgroup is always largest, so I should always get the largest subgroup. So if there was a connecting morphism, then chasing along the zigzag, I mean, if there was a connecting morphism such that direct image along it is the same as chasing the subgroup along zigzag, then chasing along zigzag would have these two properties, that chasing smallest will result in smallest and chasing largest backwards will result in largest here. And then we say, okay, if a zigzag satisfies those conditions, that smallest and largest subgroups are invariant under chasing forward and backward respectively, then such a zigzag must necessarily admit a connecting morphism. And that turns out to be true, quite remarkably. And the way it's proved is that this condition that chasing, let's say, smallest to smallest from here to there, chasing smallest gives smallest in here, that condition turns out to force, remember chasing this way, we said it will be up and down, and that turns out to force arrows here along that path that are directed against the direction we're interested in, specifically these red arrows here. They will turn out to be isomorphisms because smallest subgroup chased from here to there still gives a smaller subgroup there. So these are isomorphisms, so we can kind of remove them. Imagine we have equalities here. And the other condition that inverse image of largest is largest forces all the arrows that are incorrectly directed here to be isomorphisms. And when we take them off, we're left with arrows that always go in the same direction, and we should just compose these arrows. And that composite will be the connecting morphism we were claiming that exists. And moreover, direct inverse images along that composite will match chasing along the zigzag. So here I have another slide. Well, we have another slide here where we explain why is it so that chasing along the top is the same as chasing along the bottom in these diamonds. It's a calculation that's shown here, but I think because of time, we're not going to go into that right now. Okay, so back to you, Amartya.
Thank you, Zurab. Okay, so once we have this pyramid and we can do this chasing of sub-objects to get the connecting homomorphism between groups, now we can apply this theory which has been developed through this pyramid, and let us take this specific diamond isomorphism theorems in the classical group theory. So what we wanted to prove that we have these two subquotients of subgroups on the left and the right, and we wanted to prove them isomorphism. And the first thing what we need to consider is to construct a zigzag, as Zurab was explaining. So zigzag is nothing but the homomorphism in different directions, so may not be all in the same directions. And then we do these chasings 4 times. So let us take another examples, which is less familiar, which is called Maclaurin's isomorphism theorem in Maclaurin-Birkhoff's algebra book, which has been formulated to, and it's a little bit more general versions of this, one of the conditions of the Noether isomorphism theorem. So here, 2 things need to be proved. One is this: if W is normal to X, then the image is also normal to the corresponding image. And finally, we have this isomorphism between this subquotient X over W to image of X to image of W. So let us just concentrate on the second part of the theorem. That means to prove that isomorphism. Okay, so for that, what we need to first construct a zigzag. How to construct a zigzag? First, what is given to us? We have been given a homomorphism between A and B. So we have this, the middle one. And what is next is given. What is given is X over X slash W, and the other side is Fx plus W. So these 4 things are given. Okay, so it is natural to expect that if we have a subquotient Fx over Fw, the next group should be Fx slash 1, because then we get the projection map and we get the quotient on the other side. So we get this new group Fx slash 1. Similarly, since we have X over W on the left hand side, it is expected that X over W came as a projections of getting killed this subgroup W from X over 1. Okay, very good. So once we have X over 1 and Fx over 1, and these two are nothing but we can attach them with the corresponding original group C and B by their corresponding embeddings. So we have actually a zigzag in a different directions of these arrows. Now, as Zurab mentioned, first we need to get a connecting homomorphism from X over W to Fx over F of W. And for that, what we need to do, that we need to chase the smallest sub-object from the left-hand side of X over W, and we must be sure that it reaches when on the right-hand side of Fx over F of W, it must be 1. So that's simple, because if we take the smallest sub-object on X over W, which is the W, and then when it landed up at A, then that's nothing but the W, because it is a subgroup of this group A. And then if we take the image of it through F, then it is F of W, and then we simply take the inverse image of F of W under this map of embeddings on the right-hand side. And when we land it up on the other side, that becomes 0, because F of W is in the quotient on the subquotients expressions on the right-hand side. And similarly, when you chase the largest subobject from the right-hand side, Fx over F of W, and it becomes, because we have this projection, so naturally it becomes Fx over 1 on the second stage, and then it should be Fx in as a subgroup of B, and then we take X on the left-hand side, and then we landed up to X over 1. So the first 2 chasing actually gives us the connecting homomorphism. Then what remains is to show that it's a kernel is trivial and it's a surjective. And for the kernel is trivial, the last one, which is this 0 subobject, as Zurab mentioned in the very beginning, the definition of kernel, and when that should landed up with 1. And for the surjection part, which is the largest subobject, which is X over W, and it landed up with this Fx over F of W. So this is a typical example how to directly use this chasing process. And of course, this can be proved using universality, but in some sense, it's much simpler just to follow this algorithm and chase this 0 and 1 in the sense of largest and smallest object of the back and forth, and we can get connecting morphisms as well as isomorphisms. Okay, so with this Maclaurin's isomorphism theorem, now finally, Zurab will tell further applications in other structures and references. Over to you, Zurab.
Okay, so by applications, we mean the contexts to which this theory can apply. And also, when you apply a theory to a context, it means that so the process is just to check that the axioms hold, of course, and the axioms are not too many, and they're very, very basic facts. So it shouldn't be difficult to check that the axioms hold. And once you do that, then you know that all the apparatus of homomorphism theorems can automatically be transferred because we are able to establish that in the general theory. So there are 3 types of contexts in which we can apply this. The variety of contexts is really huge. Each of these 3 might themselves be huge, particularly this one, which is the context of semi-abelian categories. So for example, vector spaces, modules which are already abelian categories that belongs to, it's kind of covered in MacLean's original duality for groups situation. Then we have non-abelian groups, which is the case in which the question was open, and rings without identity, co-commutative Hopf algebras over an algebraically closed field of characteristic 0. So we know that our theory applies there simply because we know it's known, established by different authors, that each of these mathematical structures give rise to a semi-abelian category, and we have a proof that every semi-abelian category will be an example of our context. There are hating meet semi-lattices there, compact Hausdorff groups. Topological groups do not fall in our context, at least we don't know if they do or not. They're not semi-abelian categories, so they don't fall through the semi-abelian context. But compact Hausdorff topological groups are semi-abelian, so they fall in our context. And also many other group-like structures. You can basically have any kind of algebraic structure as long as you have group operations inside it. It should work. So if new type of group-like structure will arise tomorrow, somebody would want to pioneer investigation of some new type of structures, then hopefully our work will allow this person to be sure that all the homomorphism theorems hold just by checking those 5 axioms. So the examples we mentioned here are the known mathematical structures, of course. Then the other stream of field of examples is given by mathematical structures which form exact categories in the sense of Marco-Grandis. Vector spaces and modules are also among those, but we also have projective spaces which wouldn't form a semi-abelian category because you might not have products there, and graded abelian groups for the same reason, and modular lattices and modular connections for the same reason. And then there are also examples covered by our theory which do not fall under these two known contexts. So these two. So homomorphism theorems in these contexts have been known. So it's not, we're not the first to say that that they hold in this context. So homomorphism theorems for semi-abelian categories have been known. For exact categories, they've also been known. What our work does is to bring these two very general categorical contexts, to bring them further together and unify them. But in this process, also new examples are captured, which are not captured by those known contexts. And some of these are mentioned right here. For example, rings with identity, which just because they're not a pointed category, they're not part of the semi-abelian context. With commutative rings and dualizing, we get affine schemes. And quite remarkably here, we have sets also forming an example of our context. And there, it's highly non-trivial in the sense that the subgroups there will not be just subsets. They have to be something much more complicated than that. And because of sets, it's something that has been proved by Francois van Niekerk. Because of sets, also arbitrary universal algebras, not just group-like structures, but any kind of algebraic structures also would be part of our context. So you can also apply theorems there. And then we will actually get the isomorphous theorems known in universal algebra for that case. And then functor categories also are there, in particular presheaps will be there. So the reach of examples is really very, very wide. And then another important thing to mention in the context of application is that duality allows to cut in half the amount of proofs we need to do. Because you prove a theorem and then you have its dual version for free because the axioms were self-dual. And this is particularly useful in homological algebra, where the fact that you could cut proofs in half in the abelian case for vector spaces, for instance, was well known. But for non-abelian groups, nothing like that was known. But now we know we can also do that. For example, in the proof of the snake lemma, when after you build this connecting morphism and you want to establish exactness of this big sequence, You only need to establish exactness here and here, and then by duality for free you'll get exactness here and here, just like this happens with in the abelian case. Okay, so that brings us to the end of the talk. These are very, very few references. We should have included much more, but we wouldn't have time to go through them, so it was no point. This page gives kind of background references, to mathematics that happened before our work, and on which our work to some extent relies. The other slide gives references for the work that was presented in this talk. Specifically, this talk is based on this paper. And the salamander story comes from this paper. And I mentioned Francois van Niekerk, and so it goes to his PhD thesis. There are also other papers that have been published on this, but we just selected the few that was more relevant for the talk. This does bring us to the end. This is a picture which we will see if we zoom out from our context and want to fit it into the appropriate categorical framework. If anyone is interested in it, we can expand on what this two-dimensional simplicial object represents and how it links with our theory. And the last thing I want to say is to announce that the 5th BRICS conference will take place in South Africa at Stellenbosch University next year. A more proper announcement of this will also happen at the end of the conference. Thank you very much.
Thank you very much.
Yeah, for a very good, inspiring talk, and essentially explaining how some sort of an axiomatization, etc., helps you in proving these homomorphism theorems in homological algebras. And I would now like to ask the audience whether they have any questions or comments. Offline audience who are present. Somebody has raised the hand, Andrew Guy. Can you unmute him so that he can probably ask the question?
Thank you, Chair. I just wondered, Zurab or Amorto, if you could say a bit more about the bit at the end, the transition from sets to universal algebras that you mentioned.
Right. So if we take the category of sets, categorically speaking, a form can be presented as a functor into your category. By the way, duality means dualizing this functor. And you take any variety of universal algebras, you have a forgetful functor. So the form that we found over the category of sets that satisfies these axioms is such that when we pull it back along the forgetful functor, so this is your variety of algebras, and this is the forgetful functor. When we pull this back, we get a functor here. And Francois showed that that functor will still satisfy the axioms. And so this way, because sets is nicely behaved, then it turns out that any category or any variety of universal algebras is also nicely behaved, which is something that was quite fantastic for us because I mean, previously, the idea was that these isomorphism theorems have to do something with kind of group likeness of algebraic structures, despite of the fact that isomorphism theorems with congruences have been known for universal algebras. But now this really shows that the group-like structures here has little role. It's really something that's applicable across all over algebra, basically. Does this answer your question, Andrew?
In fact, that is precisely what I also wanted to ask. I mean, somehow the sets don't seem to have a structure. I mean, you said they still have a structure and you can still apply your theorems.
Yes. Well, sets still form a category. We have functions between sets that allow us to formulate homomorphism theorems.
You always go from the elements to the homomorphisms.
Yes, so in the place of homomorphism,
it gives you a little more way easier to handle. Any other questions? Comments? Okay. If not, let's thank both the lecturers for such a beautiful, lucid talk.
Thank you so much.
Now back to the organizers.
Yeah, so we close the session for the day. And tomorrow we're going to meet again at 9 o'clock, and we have a lot of contributed talks from the young Indian mathematicians. So I would encourage all of you to join. This would be followed by the closing ceremony at Indian time, 12:15 p.m. And I request all of you to join for that as well. Thank you.